This video is going to work through vector components. What if I have a vector that doesn't point completely in the x direction or in the y direction? I can draw a vector that looks like this. And maybe I can say this is 5 meters and 37 degrees. If I'm asked for the direction, I might say it's up and to the right, which is exactly how I'm going to handle this thing. So I want to ask how far up and how far to the right. To do that, I'm going to need some basic trigonometry. Now, if trigonometry is a word that brings up some almost repressed memories or some groaning or maybe a little bit of a shudder, I do want to put your mind at ease. The only things we're going to need for this course are Pythagorean theorem, sine, cosine, tangent. And even there, we're only going to use them for right triangles. We're not going to do law of sines, law of cosines, that kind of thing. So back to this triangle. This triangle has a magnitude of 5 meters and it points up and to the right. It points a little bit more to the right than up, but we can figure out just how much of each. What we do know is that the vector makes an angle of 37 degrees with the positive x-axis. So I will draw in some axes. Let's say this is my positive x-axis, and this, which of course goes right through that writing, is my positive y-axis. For whatever reason, just about every book that you'll ever encounter uses Greek letters for angles, and this letter is theta. So let me write that for you. This is a lowercase theta, and we use it to just mean angle measure. The other one that we'll use from time to time looks like this, and this is a lowercase phi. A little bit easier to have names for these symbols than to try and just come up with something. Moving on, we have different mnemonic devices for remembering the basic trig functions. SOHCAHTOA is a popular one. SOHCAHTOA, which looks like this. The sine of an angle is the opposite over the hypotenuse. Sine, opposite, hypotenuse. I want to take this vector and break it into two components. One that points along the x-axis, one that points along the y-axis. When I do that, I will have made a right triangle. So I'm going to go right here, one component along the x-axis, one component along the y-axis. If my original vector was v, then this is going to be my vx, and this is going to be my vy. And look at this, I have made a right triangle. The original vector is the hypotenuse, and the x and y components make up the legs of the triangle. So let's start with the x component. The x component is connected to my angle theta, and that makes that the adjacent side to my angle. For the adjacent side, I can use either, going up here to my list, I can use either cosine or tangent because those are the ones that have adjacent side in there. I'm going to use the cosine because I have the hypotenuse. So what I can say is that the cosine of my angle, cosine theta, is equal to the adjacent side over the hypotenuse. I can kind of plug in a couple of things. The cosine of 37 degrees is equal to the adjacent side, Vx, divided by my hypotenuse of 5 meters. If I am trying to solve for Vx, I'm going to multiply this side by 5 meters, which means I have to multiply this side by 5 meters. Those cancel, and I am left with Vx equals 5 meters times the cosine of 37 degrees. The cosine of 37 degrees, if I punch into a calculator, will work out to be 0.8. So I get 4 meters for my Vx. I'm going to do a similar thing for the y component. I'll move this over a little bit. For the y component, I know that the sine of my angle is equal to the opposite side over the hypotenuse. So the sine of 37 degrees is Vy. That's my opposite side right here, over the hypotenuse, which is my 5 meters. I'm solving for Vy, so I'm going to multiply by 5 meters. That's going to cancel, and I get that my Vy is equal to 5 meters times the sine of 37, which is 0.6. So I'm going to get 3 meters. There's my Vy. I have now broken this vector up into components. What I had was V was 5 meters at an angle of 37 degrees. Or now, four meters in the x direction and 3 meters in the y direction. I also want to be able to do this backwards. What if I have the components and I need the reconstructed vector? Here I have a couple of vector components. Maybe I'm standing here and I am going hiking. I know that the place I'm trying to hike to is 8 miles to the east of me and 15 miles to the north. So it's here somewhere. I'm going to write those directions. So here's 8 miles. And then I'm going to say, if I were walking this, I could go 8 miles east and then go 15 miles north. I would like to know, how far is it from me if I go directly there, and how do I do it? So I'm going to lay out these vector components head to tail. That's what I just did, so that one picks up where the other one left off. Now I have a path from my starting point to an ending point. I'm going to connect my starting and ending point with a single vector, which is now my unknown, so I'll do that one in red. And I have, again, made a right triangle. This is my Vx. This is my Vy. I want to figure out this diagonal, the hypotenuse, so I am going to use Pythagorean theorem to get there. Pythagorean theorem says a squared plus b squared equals c squared, where c has to be the hypotenuse. So I'm going to put in the values that I've got. This is Vx squared plus Vy squared, and those could be reversed, that's okay, equals V squared. This means V is going to be the square root of vx squared plus vy squared, which is the square root of 8 meters squared plus 15 meters squared. 8 squared is 64, 15 squared is 225. If I add those together, I get 289. And the square root of 289 happens to be 17. V is 17 meters, or 17 meters, I got stuck on it, miles. That's part of it. The other part that I need is the angle. I'm going to draw in an angle, and I like to draw in the one that connects to the x-axis. So there's that. I think I'm going to use tangent this time because I haven't used it yet and I don't want it to feel left out. Or if you like a more scientific reason, the x and y components were given, and it's generally a better idea to use the given quantities than it is to use calculated quantities, which tend to be rounded. In this case, it's not rounded, it happens to come out to a completely whole number, but habit. The x component is connected to my angle, so this is my adjacent side. The y component's not connected, so that's my opposite side. So I can say the tangent of my angle is equal to opposite over adjacent. So it's equal to y, well, vy over vx. Tangent of my angle is 15 miles over 8 miles. But I don't want the tangent of my angle, right? What I want is actually the angle itself. So how do I do that? Well, I'm going to take the inverse tangent of both sides, or if you are a purely math person, the arctangent of both sides. Over here, the inverse tangent of the tangent of something. Those are, well, inverse functions, so they cancel. So I get theta equals the inverse tangent of 15 miles over 8 miles. If you are using a handheld calculator, you are probably going to say shift and tangent or second and tangent. If you're using a computer, you might type atan, 15 over 8. They mean the same thing. So when I do that, I get the inverse tangent of this angle, which is 62 degrees. I'm going to go back to my triangle. My angle here is 62 degrees. I started off facing east. I turned toward the north. So my vector, which was given as 8 miles x and 15 miles y, can also be expressed as 17 miles at theta equals 62 degrees, and I started facing east, turned toward the north, so this is north of east. That's it. That's breaking vectors into components, and it's taking vector components and reconstructing a vector, so going both directions with it.